Hello, and in this video, I'd like to review a step-by-step solution for an air standard diesel cycle. And the first thing I'd like to do is compare and contrast a diesel engine to a gasoline engine in a crash course type idea, and then we'll move ahead to step-by-step working through a diesel cycle analysis. So here we go. Here's a cutaway view of a real diesel engine. And what I want to cover next is compare and contrast a diesel air standard cycle with the Otto, which is a gasoline model for a gasoline engine cycle. Then we'll look at two specific diesel cycle analyses. One with, well, of course, ideal gas, with variable specific heat model. And then we're going to do exactly the same problem using the constant specific heat model. And we're going to compare and contrast both of those approaches. So here's the crash course comparing a diesel cycle with the Otto cycle. Okay. Well, so here's a couple of images of a diesel engine and a gasoline engine. And wow, they look very similar, don't they? Here's cutaway pistons and cylinders all in line. Here's an inline six-cylinder engine. Similarly, pistons and cylinders all connected to a rotating shaft that's delivering rotating energy to the wheels of a vehicle of some sort, whether it's a truck or a car. So they look very similar. How are they similar and how are they different? Okay, let's look at how the diesel engine and the gasoline engine are similar and how our analyses will be similar and different. Well, for both of these, since the air is going to be, our model is the air is fully contained in a piston and cylinder, our analysis is going to be for a closed system, a fixed mass of air in a piston and cylinder. Now, we use a thermodynamic model of the real world, and we do pretty good at terms of modeling thermodynamically. Let's look over here. So our thermodynamic model is going to be contained within this black box, rotating clockwise direction, showing positive net work coming out. And for our analysis, notice here, there's no dots on the schematic diagram. What we're going to do in our analysis is we're going to analyze one single cycle of the air contained within the piston and cylinder. That's our approach. Now, how do we model we know we've got internal combustion engines. So we've got fuel coming in and air coming in, and there's combustion, and then there's exhaust, and there's all that kind of stuff going on. We're not going to model all of that. What we do is we model this combustion process as a heat addition process, QH. And so up here in our schematic QH, this is our thermodynamic model of the combustion process. Okay, this is how both the diesel cycle and the Otto cycle, modeling the gasoline cycle, how they're similar. Also, measure of performance, the thermal efficiency, the energy sought, W net, over the energy that costs us, QH. We got to buy that fuel, okay? That's the definition of thermal efficiency for both cycles. And also some new jargon, especially for those of you interested in automotive engineering, the mean effective pressure, the MEP, the mean effective pressure, is going to be the net work for one cycle divided by the displacement volume. That's the maximum volume minus the minimum volume in the piston and cylinder, mean effective pressure. This is your textbook equation 9.1, and the units of mean effective pressure will be kPa, kilopascals, or pounds per square inch. Okay, now let's do a quick look at how the diesel cycle and the Otto cycle are different. Fuel. Well, the diesel cycle uses diesel fuel and the Otto cycle uses gasoline. So these are chemically two different fuels. Now, one thing that students need to be very aware of, many students know this because of their experience, their practical experience. Some students don't know this. A diesel cycle does not use spark plugs. The gasoline engine does. The reason that the diesel cycle does not use a spark plug is because the pressure gets high enough to initiate the fuel and air combustion. And so this is called a combustion ignition system, whereas the gasoline engine, we call it the spark ignition system, where it takes a spark, an electric spark, to initiate the combustion of the fuel in the air. That's a big difference. Now, so the speed of combustion, how are they different between diesel and auto? Well, I hope that your common sense, if you imagine a combustion process, combustion that's started by pressure, that combustion is going to be slower than instantaneous. Whereas if you initiate combustion with a spark, it's almost as if that combustion happens instantaneously. And for the Otto cycle, we consider the heat addition to be instantaneous. Whereas in the diesel cycle, that's what we're going to analyze here, we're going to model the heat addition as constant pressure. So the heat addition model for our air standard analysis for the diesel cycle, heat addition is modeled by a constant pressure process. For the gasoline Otto cycle model, we model the heat addition as constant volume, like instantaneous. The volume, the combustion happens so fast, the volume doesn't have a chance to change by moving against the piston. Okay, so now we're getting close to starting our worked out example problem. These are screen clips right out of your textbook, the air standard diesel cycle model. Well, let's look at the physical setup first. Here's a very decent sketch. Recognize that we're going to be analyzing a closed system, air contained within a piston and cylinder. Okay. Recognize that we don't have a spark plug for our diesel cycle. We have a fuel injector. Fuel is squirted in as the air is compressed. Okay, let's look at our pressure volume diagram. So powerful when we're analyzing closed systems because we can visualize work for each process. Okay, so we're going to start at state one where the volume is biggest, bottom dead center, biggest volume. We're going to go through the compression stroke, isentropically, reversibly, and adiabatically. No heat transfer, no friction. Okay, reversible adiabatic compression up to a high pressure. Okay, at that point, the fuel is injected in, and at that very high pressure, we get the combustion, but it's not instantaneous. That's why we have this constant volume expansion where we're adding heat. This process 2 to 3, that's where we're adding heat at constant pressure. Look at this. Work is bigger than zero. You can see it on the PV diagram. Work is integral PdV. Oh, I didn't mention, pardon me, the work from 1 to 2, the isentropic compression. Do you see how it's going to be a negative number? We're integrating right to left. Work is integral PdV. It takes work to compress the air. All right. Now let's jump to 3 to 4. This is the power stroke. The power stroke, 3 to 4. This is where we're really driving the shaft to produce power to deliver to the wheels, the tires of the car. Isentropic expansion, 3 to 4. Okay, power stroke. And then finally, 4 to 1 in our thermodynamic model, we're saying we're rejecting heat from the air at constant volume. So this completes the cycle. I hope that visually you see, oh yeah, the net work is the area contained within this PV diagram. I think I got it. Now for jargon, some are going to know this by heart already from your practical experience. Others need to learn the jargon. R, little r, is called the compression ratio for internal combustion engines. And that is simply V1 divided by V2, the max volume, divided by the minimum volume of the air inside. And so do you see the compression ratio is fully defined by the geometry of the piston and cylinder. Now we're going to study the diesel cycle model, and we've got another piece of jargon called the cutoff ratio. Look, and that's simply defined as R sub C is V3 over V2. Okay, that's, in other words, the volume at the end of the heat addition model, the constant pressure expansion process. V3 over V2 is called the cutoff ratio. You need to commit these two jargon definitions to your memory, or at a minimum, get them on your formula sheet. Okay, so now spend a little time. I guess I have to apologize, a little crash course time before we undertake the numerical example problem. An air standard diesel cycle operates with a mass of 0.65 kilograms contained within the piston and cylinder. At the beginning of the compression process, that's going to be state one, the pressure is atmospheric pressure, 100 kPa, and atmospheric temperature, 290 K. Very typical of the real world. The compression ratio is 16, very typical of a diesel engine. The maximum temperature in the cycle is 2200 degrees K. That's hot and typical, representative of a real diesel engine. We want to model the air as an ideal gas with variable specific heat. Translation, use table A22. Air, variable specific heat, use table A22. Now we've got a laundry list of things we need to find. The displacement volume, the cutoff ratio, the heat added, the thermal efficiency of the cycle, and finally, the mean effective pressure. So we have a laundry list of things to find. This could be typical. This is typical of a homework problem, and it's also typical of bits and pieces of a test problem. So be very aware that in a test situation, you will not have time to do this entire analysis. You will be asked for bits and pieces of this analysis. So you got to be able to go through the whole thing so you're prepared for a test. Okay, so here's our approach. And I tried something a little different this time, more of a visual approach rather than a step-by-step definition of what you'll do. Well, we are going to analyze each process in the cycle. We're going to analyze 1 to 2, and then 2 to 3, 3 to 4, and 4 to 1. And we're going to tabulate Qin for each of those processes, and we're going to tabulate W out for each of those processes. Make sense? Okay. So I've sort of set things up. 1 to 2, W out is a negative number. 2 to 3, W out is a positive number and easy. The work out 2 to 3, easy. 3 to 4, a little tougher, but positive. Okay. And then 4 to 1, what's the work done 4 to 1? 0. Okay. So we're set up. What tools are we going to use to analyze each process? We're going to use the ideal gas equation of state, PV equals mRT. We know M. We know R for air. Okay. We're also going to use the first law for each process. Q in minus W out equals delta U equals, and that equals the mass times little u final minus little u initial. Once we've done that analysis, we're going to take some shortcuts. We're not even going to bother to analyze process 4 to 1. Okay. We will have enough information to determine the thermal efficiency. W net, we'll add all these numbers up, divided by QH. We're going to pick out Q from 2 to 3. Okay, so there we go. That's the approach. We're going to go through and do all the numbers so that you can see how to work through every single number on this diesel air standard cycle analysis. Okay, where do I start? This is a common question that students ask. Where do I start? How do I start? You threw all this information at me. I'm lost. Where do I start? Of course, start with a sketch, and the PV diagram is the key thing to start here. And so when you study what you have, you will discover that you need to start at state 1 because you have P1, you have the mass, you have R, T1 is given. You think about, let's see, what do I have that involves those things? I got the ideal gas equation of state. The only unknown is V1. That's where I will start. So here we go. The mass, 0.65. R for air, 0.287. You either know that in your head or you go R bar divided by the molecular weight. R is 0.287 kilojoules per kilogram degree K. P1 given, keep it in kPa, and T1 always, always in absolute temperature. So plug and chug, get your calculator out to solve for V1 is 0.541 cubic meters. That's the ideal gas equation of state. Okay, we're getting somewhere. Now, let's see, displacement volume. Okay, you have to be thinking now, so it's not obvious. What are you given in the problem? And you're given a compression ratio of 16. Okay, here we are, compression ratio of 16. What's the definition? It's V max over V min, okay? I just found V1. That's the maximum volume. That's at bottom dead center of the piston and cylinder, bottom dead center, okay? Where's the minimum volume? It's at top dead center, okay? So you're given that. So now V2 is easy, isn't it? It's 1/16 of V1. So immediately, displacement volume, if this were a quiz question, at least you can get this far, okay? Subtract one from the other to get 0.5072 cubic meters is the displacement volume. Got it. At least that gets you moving and solving the problem. Looking ahead, we're gonna now study process 1 to 2, which is reversible and adiabatic. It is an isentropic process, and we have to refresh our memories quickly on when we have an ideal gas with variable specific heat, reversible adiabatic, isentropic, and variable specific heat. We go to table A22 for air, and we're going to be using either P sub R or V sub R, whichever is the handiest, whichever is the easiest. But recognize these two columns only apply to isentropic processes. So here's our choices. PR2 over PR1 equals P2 over P1. We don't have P2, so that's, will the VR help us? Okay, let's see. VR2 over VR1, that's going to be table work. How about V2 and V1? We've got that. V2 and V1 over V1 is 1/16. We will select the relative specific volume to work with. Table A22. That's why. That's the why we do what we do. Okay, so we're going to go to table work. We're going to start at T1, and we will write down U, because we're going to use the first law. If you're going to use the first law, always write down U, and then go and write down VR1. So I've got 676.1, which is VR1. Just write it down. And then U1 is 206.91 kilojoules per kilogram. Write that down. It's going to be very handy. So now we're analyzing process 1 to 2, isentropic process 1 to 2. We recognize, okay, so here's our governing equation. VR2 over VR1 equals V2 over V1. We just wrote down VR1, so we can solve for VR2. Look at that, we've got V2 over V1. So VR2 is 42.26. What good does that do us? We go back to table A22 to shop around for 42.26. All right. Oh, it's in between two numbers. So I'm going to have to back solve. I'm going to have to interpolate for T2. I'm going to need T2 in my analysis. Interpolate for T2 somewhere between 820 and 840. And also looking ahead, we're going to need internal energy, little u. So we'll interpolate for both of those to get that U2 is 622.73 and T2 is 837.3 degrees K. So we're getting somewhere. Okay, so at least we found T2. All right, so now we've got, it does, let's see, Process 1 to 2, reversible and adiabatic key. We can use the first law then to determine the work, find the work done from 1 to 2 using the first law. We wrote down U1, we wrote down U2, we have the mass. Okay, so the work out, little U1 minus little U2 is negative 415.8. Okay, first law. Okay, Q is 0 for 1 to 2. And then the work, so we'll multiply the little work out by M to get capital work out in kilojoules, negative 270.28. For this analysis, I'm getting both, but it's going to pay you moving ahead. You're going to need W out in kilojoules, so that's why we're multiplying by mass. We're going to need P2. If you think back about your PV diagram, you need P2. So when I was solving this problem, I remembered the jingle for an ideal gas. P1V1 over T1 equals P2V2 over T2. I remembered that. And so I've got everything except P2. P2 is the only unknown. So I went and looked up all my numbers, wrote them down, and solved for P2, 4619 kPa. And then it came to me after, God, that was a lot of write down stuff. Is there an easier way to find P2? And the answer is absolutely yes for this problem. How about the ideal gas equation of state? PV equals MRT. I've got all these things. So this alternative method that I wrote down is really much easier, but identical way to solve P2. Okay, either way can work, but you got to find P2. Because, okay, what's the benefit of that? Look up here at your PV diagram. If you found P2, work becomes very easy. And also the cutoff ratio becomes pretty easy. Let's see, P3 equals P2. Okay, T3 is given. T3 is given, so I wrote that down. And then I used my jingle again to solve for V3, capital V3. Now, same thing applies. Look, this was an elegant way to solve for V3, 0.088843 cubic meters. P2 V2 over T2 equals P3 V3 over T3. Just as good to say PV equals MRT, and so solve for V3, because look at this, P3 equals P2. You know the mass, you know T3, you can solve for V3. So the cutoff ratio, I had to write this down because I don't have a lot of experience in automotive engineering. The cutoff ratio is V3 over V2, so the cutoff ratio is 2.63. Okay, we're moving along. Okay, next, W out. So do you see how we're working through the cycle? The work out for process 2 to 3, easy. I've got a vision of it on my PV diagram. There's the visualization of the work from week 2 of your class. So plug and chug, right? Plug and chug. You've got P2 is known, 4619, V3 and V2 are known, and so the work out is 254.21 kilojoules. So we're moving along. We just finished process 2 to 3 for work. Now let's see, that's where the heat is added. We'll use the first law. We just got the work. Let's use the first law to find the heat added. Q in from 2 to 3 minus the work out from 2 to 3, just found it, equals M times little u3 minus little u2. And we've got all that information. T3 was given, so we looked up U3, 1872.4. Looked that up in table 822, wrote down all of our known information to get Q in from 2 to 3, that's QH, 1066.5 kilojoules. Man, seems painful, but we're on the home stretch. Next thing to do is to study isentropic process 3 to 4. Well, we'd better get the starting information for state 3. So we just found T3. Okay, T3 was given. it was given, we didn't, 2200. So we will write down U3 and VR3. We'll write those down. There they are, 1872 for U and 2.012 for V sub R. Now we can analyze isentropic process 3 to 4 to find U4. So VR4, so we do the little jingle, VR4 over VR3 equals V4 over V3. We have all that information. Use our calculator to determine VR4 equals 12.25. We got to go shopping. And we look at the bottom column, VR, here we go. We're in between 12 and 11.8. Yes. Okay. So we got to go do that linear interpolation again for U4, 992.36. Now, I found T4 as well, but you don't even have to find it. If you're doing this by hand, pencil and paper, you don't even need to find T4 because you're really looking for U4 to apply the first law for process 3 to 4. We'll use the first law to determine W out for 3 to 4, because remember, process 3 to 4 is reversible and adiabatic. Q equals 0. All right, so we found U4, we've got U3, little W out is 880 kilojoules per kilogram. Just subtract those two, multiply by the mass to get W out in kilojoules, 572.03. If I'm going too fast, remember you can download all these PowerPoint slides with a mouse click. Now we're close, we're perilously close to getting thermal efficiency. We'll remind ourselves, what does the net work look like on our PV diagram? It's the area contained within the cycle. We'll dutifully go through, let's see, the work from 4 to 1, that's 0. So all we have to do is add up these three numbers to get W net, 555.96 kilojoules. Ooh, we're getting there. Okay. So finally, we can get the thermal efficiency, the energy sought, W net over the energy that cost, QH. We've already got that done. So the thermal efficiency is 52% for this thermodynamic model of the diesel cycle. Mean effective pressure. I have to admit, I have to go back and look at the definition of mean effective pressure, which is the net work in kilojoules divided by the displacement volume, the V max minus V min. So the mean effective pressure for this thermodynamic air standard cycle for the diesel is basically 1 MPa, 1096 kPa. Complete. Okay, so there it is. That was the complete analysis of the air standard diesel cycle. Second problem is identical to the first problem. Same exact data, but we want to model the ideal gas with constant specific heat. We want to find the same laundry list of things. Why am I dragging you through this second time? Because this is going to be very professor dependent. Some professors like the constant specific heat model. Some professors like the variable specific heat model. So I'm trying to get you ready for your test, ready for a quiz. So you need to be proficient in using both approaches. Either approach will work, and we're going to compare the numeric results for both of these. So let's move ahead and repeat the same analysis, except constant specific heat. Do not use table A22. You cannot use table A22 for this ideal gas model. So our first step is to constant specific heat. We need to find C sub V because we're going to be calculating delta U, delta little u, and also we're going to need K. Remember, K for an ideal gas is Cp over Cv, the ratio of specific heats, and we're going to be using that for our isentropic analyses. So the best we can do for this problem is look up K and C sub V at 1,000 degrees K, because there's nothing higher tabulated in table A20. So we're going to say our nominal temperature is around 1,000 degrees K, and that's close enough. That nominally, the average nominal of these two is around 1,000 K. So we're going to write down K is 1.336 and C sub V is 0.855. The approach, exact same approach as we used for variable specific heat, air. Determine V1. Now this is just about a screenshot from the previous. So exact same computational approach, R for air, PV equals MRT, and you're going to get exactly the same volume, 0.541 cubic meters. Exactly the same as your first time through. Displacement volume. Let's see. Exact same approach because you're given the compression ratio. The displacement volume is going to be exactly the same, 0.5072, V max minus V min. Next thing to do is, I should have looked ahead. We're going to study process 1 to 2. 1 to 2. That's isentropic. That's the compression process. And for an ideal gas with constant specific heat, PV to the K is constant. That's our governing equation for ideal gas, constant specific heat, constant CP, which must mean CV is also constant. That means K is constant. And also for the process must be isentropic or reversible and adiabatic. This is the governing equation we use instead of using V sub R stuff out of A22. Very important that you understand that. So what we're going to do is use our handy PV to the K is constant relationship. And for this diesel analysis, look, we have V2 and V1. So we have that volume ratio. So P2 becomes easy to find. P2 is simply P1 times V1 over V2 to the K. And K is a number. Calculator work. So P2 falls right out, 4,061.7 kPa. That's P2. Now we got something else easy. If we've got P2 and we have V2 and we have M and R, it's easy to find T2. We use the ideal gas equation. PV equals MRT. Solve for T2. T2 is 736 K. Higher, we're compressing the air. Temperature goes up. Next, we're going to use the first law for process 1 to 2. I hope you're seeing the repetition. Let's see. Process 1 to 2. Reversible and adiabatic. Wow, that's handy. Adiabatic. Q is 0. Makes the first law easy. W from 1 to 2 is simply U1 minus U2. So Q minus W equals U2 minus U1. So we flip the sign. So little w is simply CV, which is constant, times delta T, T1 minus T2. So numerical work or calculator work, W out in kilojoules per kilogram, little w, negative 381.48, multiplied by the mass to get big W, negative 247.96 kilojoules. Move ahead. Okay. Find V3. Well, let's see. V3, we'll use the ideal gas law. Okay. And T3, well, where was I? We finished process 1 to 2. I got lost a little bit. Okay. How do we find V3? We know that P3 equals P2. We're given T3. We can use the ideal gas law. I see that I did my elegant way, but also you could say P3 V3 equals MRT3 to find V3, 0.101045 cubic meters. So, okay, so we found V3. So the cutoff ratio is 2.99, V3 over V2. So we had to find V3, and we did. Okay. Work out from 2 to 3. Easy. Integral PDV, P is constant. Plug and chug just like before. And work out is 273.08 because we have slightly different volumes. We numerically different number because we have numerically a different V3. There's the visualization. Process 2 to 3 is where the heat is added. Again, we'll use the first law. We just, it's easier than table A22 because we've got Q in, that's what we're looking for, minus W out, we just found it, equals U3 minus U2. Well, that's mass times CV times delta T, because CV is constant. The integral of CV dt is easy. So again, plug and chug, Qn is 1086.6 kilojoules. This is really moving fast because we can do our computations much faster. There's no interpolation to do with the constant specific heat ideal gas model. So tried and true, isentropic process 3 to 4. You must have your PV diagram to keep this straight. Okay. Solve for P4. P4 is P3 times V3 over V4 to the K. So this isn't just a formula. It's using the fundamental statement of isentropic process. Ideal gas, constant specific heat, isentropic. P4 is 431.7 kPa. So I think we're going to, next slide is going to be solve for T4. It is, okay. So we're going to use the ideal gas law, since we just found P4, to solve for T4, 1251.9 degrees K. PV equals MRT for the ideal gas. Always, always. Okay, so we solve for T4. We'll go back and we're going to use the first law for process 3 to 4, adiabatic and reversible. Adiabatic is key. And so again, first law, Qn, 0, minus W from 3 to 4 equals U4 minus U3. So remember, we're going to have this, we're going to pick up the minus sign to get the work from 3 to 4 is CV times T3 minus T4. Again, not a formula. You simply derive this after you've written the first law. Okay. So little workout, 810 kilojoules per kilogram times the mass equals big W out. This is the power stroke, 526.88 kilojoules. This is where we're really we're doing the work to drive the wheels of the vehicle. Repetition of net work, area contained within the cycle, 550, we add these 3 works that we calculated up, 551.99. We remember the definition of thermal efficiency, the energy sought, W net, divided by the energy that cost, QH, 0.508 thermal efficiency. The displacement volume, we remember the definition. I have to go to my formula sheet for my definition. Okay, shame on me. The mean effective pressure is W net over the displacement volume, or 1088 kPa. All right, so there is our full diesel cycle analysis used for constant specific heat ideal gas. So let's compare our numerical results. And so I've gone in and I've tabulated all of the things we were asked to find, and you can take a quick visual look and you see, well, what's really important? What are the important things in these analyses? Well, for an engineer, and that's performance. It's performance of the engine. And so these last 2 entries really are the measures of performance for the engine. And the difference in our thermal efficiency result is only less than 3% variability. That is good in the engineering world. So we've used 2 different approaches. We've done all of the number crunching, and we get only a 3% difference in the numerical result. That's pretty darn good, very satisfying. And in mean effective pressure, less than 1% difference between the 2 measures. So only small variation in the 2 key performance measures. And so these 2 models are quite comparable. Even when the temperature difference was huge, the minimum to the maximum temperature for this situation was a huge difference. Remember, 2200 was the max and 290K was the min. So even with a very large variation in air temperature change, we get numerical results. Now, some students have said, why? There's a formula given in the book for the thermal efficiency. Why do I need to learn how to go through each step? Why? That's a waste of my time. Well, my answer is that it's not an overall waste of your time because you're preparing yourself to do well on the test. And in the test situation, you're not going to be asked to simply apply a formula and get a result. That's freshman or sophomore level. So at a higher level, you're going to be asked how much heat is added, how much heat is added. And then you're going to go gulp. But I have this nice formula for thermal efficiency. Well, that's not what you were asked. So in a test situation, you're going to be asked a little bits and pieces of these problems. And that's where it's important that you know how to do each step. Okay, so quick recap. Remember, for an air standard diesel cycle or the Otto cycle or other internal combustion engine models, you're analyzing a closed system analysis, not an open system. That's different. So open system analyses was for steam power plants, okay, and some others that are coming up. Closed system, internal combustion engines. Remember that the compression and expansion processes for these are considered to be isentropic, reversible and adiabatic. For the diesel engine, the constant pressure heat addition and expansion model, that's what models the compression ignition process. And for the diesel cycle, 3 processes involved work. On the Otto cycle, there's only 2 processes that involve work. And you can see that in doing your homework problems. But for the diesel, 3 processes involve work. And so that's it. So I have gone through step by step how to analyze the air standard diesel cycle. I hope that helps you. And I know that it's very uncomfortable and it is time consuming to go through every single process step, but it will pay off for you as you're preparing to take a test or exam. I hope that helps, and we'll see you in the next video.